So, um, so you should have gotten a couple homework assignments back over the weekend. Forget which ones I did actually. Um, but if you didn't get the grades on those, let me know. And don't forget about the upcoming assignments here for Monday, Tuesday, and Wednesday. Section 3.3, 3.5, 3.6. So last time we went over section 3.6. So let's do some of the exercises from that section. So section 3.6. So 1542, every third problem. Here it is. Okay. Um, mm-hmm. 43, 45, 49, 51, 57, 89. Okay, so number, say, 43. Okay, sketch the graph of the function of the rational function r of x is 4x minus 2 over x plus 2. Okay, so remember the features that we discussed about rational functions. There's these horizontal asymptotes and the vertical asymptotes. So for the horizontal asymptote, okay, we look at the degree of the top and the degree of the bottom of this rational function. So the degrees on top and bottom are the same. So we have horizontal asymptotes so you look at the highest power of x on the top and bottom, and you look at the ratio of those coefficients. So at y equal to 4 over 1. All right, so just at y equal to 4. If the degree on the top is less than the degree on the bottom, then you have a horizontal asymptote at y equal to 0. Okay, y equal to 0 just being the x-axis. And then vertical asymptotes, all right, you look at where the bottom is equal to 0 and the top is not. Well, the bottom is equal to 0 at x equal to negative 2, all right, which for at x equal to negative 2, the top is not equal to 0. It's equal to negative 10. All right, so at x equal to minus 2. And Other features that help to sketch the graph of this function. First, the x-intercept. Where is the top equal to 0? Well, that's where 4x minus 2 is equal to 0. That's at x equal to a half. And the y-intercept, okay, that happens where x is equal to 0. So that's at r is equal to 0, or r of 0, excuse me. It's minus 2 over plus 2, which is minus 1. So horizontal asymptotes, vertical asymptotes, x-intercepts, y-intercepts. And then we want to know about positive and negative. Okay, so we've got these points where the top of the rational function is equal to 0, and these points where the bottom is equal to 0. And these are special points where the rational function can flip from being positive to negative. Okay, so we have the x-intercepts, that's where the function is equal to 0, at x equal to a half, or sorry, where the numerator is equal to 0, at x equal to 1/2. And we have a vertical asymptote at x equal to negative 2. That's where the bottom is equal to 0. So at these collections of points where you have vertical asymptotes and x-intercepts, that's where this rational function can flip from being positive to negative. Okay, so now we look at these intervals and see, well, is the function positive or negative on those intervals? So we test a point in each interval. So here we'll try x equal to minus 3. So for minus 3 of negative on the top, negative on the bottom. So negative over negative, that makes the function positive. Inside here, we've got x equal to 0. So we're negative on the top, positive on the bottom. So the whole function is negative. And for x bigger than a half, try x equal to 1. Positive on the top and the bottom. So the rational function is positive. Okay, so we've got all of these features for the graph of this rational function. Other than these features, the graph is nice and smooth and unbroken. Okay, and using that assumption and all of these features here, we can get a nice sketch of what this graph looks like. All right, so horizontal asymptote at y equal to 4. So we'll say right about here. X-intercept at x equal to a half. So right about there. Y-intercept at y equal to negative 1. So I guess that'll be right about here. So let's move the 1/2 closer. The x and y axes don't have to use the same scale, but we'll try to do that here. So y-intercept, x-intercept, horizontal asymptote, and then vertical asymptote at x equal to negative 2. Vertical. And then we have positive and negative behavior. So negative before x equal to negative 2, or sorry, positive here, negative here, positive here. So maybe we can mark that on the x-axis. So the graph is the function is positive here, negative in this interval, and then positive in this interval, and then we've got these asymptotes as shown. So we have to climb up or down the vertical asymptotes, and we have to sort of hug the horizontal asymptote. And then we're positive here, so, well, over here it's got to look like this. In order to be nice and smooth and unbroken, it's got to be curved in this kind of way here. And then down here, it's negative, and crossing the y-axis here, x-axis there, and then positive after that. Let me zoom in here. And then it has to hug the horizontal asymptote. So something of this sort. Right, positive here, negative here, positive here, x-intercept, y-intercept, and the various asymptotes shown, where the graph has to hug those asymptotes. It's getting closer and closer to those numbers. Right, it's climbing up to infinity here, climbing up from negative infinity here, and then approaching 4 as x gets very large and positive or very large and negative. Okay, so that's one of the examples. Let us look at another one of these. How about number 49? So sketch graph of 4x minus 8 over x minus 4, x plus 1. All right, the degree on the top is 1. Degree 1 on the top is, the degree on the top is 1, and the degree on the bottom is 2. Right, this is degree 1, that's degree 1. When you multiply them together, it becomes degree 2, because we'll have an x squared there. All right, so the degree on the top is less, strictly less, than the degree on the bottom. Okay, and that tells you that your horizontal asymptote is at y equal to 0, which is the x-axis itself. So the degree on top is less than the degree on the bottom. So horizontal asymptote at y equal to 0, which is the x-axis itself. And vertical asymptotes okay, that's where the bottom is 0, but the top is not. So that's at x equal to 4 and x equal to negative 1. So x equal to 4 and x equal to negative 1. And you'll notice on the top, if you plug in x equal to 4, you get 8, which is not 0. X equal to negative 1, you get negative 12, which is not 0. It has to not be 0 on the top, as well as 0 on the bottom to have that vertical asymptote. When it's 0 both on the top and the bottom, well, you know, there's other considerations. You still might have a vertical asymptote, but you might not as well. You know, I don't think it's necessary to discuss that. You'll actually talk about that in Calculus 1, when you get there, like what graphs like that look like. So, all right, so horizontal asymptote, vertical asymptote. Let's look at x-intercepts and y-intercepts. Okay, well, the y-intercept, okay, that's just at x equal to 0. When x is equal to 0, that's where the graph is touching the y-axis. So that's at negative 8 over negative 4 times 1, right, which is going to be 2. X-intercepts that is where the numerator is 0 and the denominator is not. Well, numerator is 0 at x equal to 2. This y-intercept, this is at y equal to 2. And we also have the x-intercept where the numerator is equal to 0. So that's at x equal to 2. All right. So first you have these 4 features: horizontal asymptotes, vertical asymptotes, y-intercept, x-intercept. And then, we want to look at positive and negative behavior for this function. So we take the x-intercepts and the vertical asymptotes. That's where the numerators and denominators are 0. We don't worry about those points themselves. We just want to know about the intervals in between. So this is at 2, 4, and -1. -1, 2, and 4. And so now we want to look at these intervals. Okay, what's going on inside these intervals? So we test a point inside these intervals to find out about being positive or negative. So at x equal to -2, say, negative on this one is negative, that's negative, that's negative. So it's negative over negative times negative, so the whole thing is negative. Here at x equal to 0, this is negative, negative, positive. So we have negative over negative times positive. So the whole thing is positive here. Between 2 and 4. So at, what number am I doing? 3. So at 3, 12 minus 8 is positive. This one is negative, positive. So positive, negative, positive. So the whole thing is negative. And then in this interval, everything's positive. Okay, so we've got positive and negative behaviors, x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, and then we put all that together and get a sketch of the graph. Let me use my line tool here.
Are you recording?
Oh my goodness, I didn't start the. No, I did. Very good. Thank you for reminding me, but yes, I did. All right. Yes, it's like that. I don't know if you've ever experienced it. When you leave your house in the morning and you're wondering, you close the garage door, you push the button for your garage door opener and closer, you drive away, and as you're driving, you think to yourself, "Did I close the door?" You have to turn around and go back just to make sure. Turn the oven off exactly. Did I start the recording during lecture? All right. So vertical asymptote, also horizontal asymptote is the x-axis, so nothing actually to draw there. Vertical asymptote at x equal to -1 and 4. And x and y intercepts at 2 and 2. So 2 here, 2 there. All right, and positive and negative behavior. So negative, positive, negative, positive. So negative, positive, negative, and positive. Alrighty, so negative horizontal asymptote on the x-axis, vertical asymptote there. So some sort like this. All right, here, vertical asymptote here, and then we've got these intercepts. So now here there's definitely an interesting feature of the graph that we're not going to be able to figure out where it is. There's what's known as an inflection point. An inflection point is where you change from curved upward to curved downward. And it doesn't always have to be on a downward slope. It can be like both on an upward slope. So these inflection points. And for that you need calculus to figure out where that inflection point is. But here, and you have to have it because in order to climb up or climb down, depending on which direction you're going, a vertical asymptote, it has to be curved a certain way. I mean, it can't be curved that way because you're going to hit it, right? And it can't just kind of climb upward and be curved down. And similar sorts of things here. It's got to be curved down in order to slope down the vertical asymptote there. And then positive here, so it has to look like that. So there is that inflection point. We don't know where it is, but I mean, that's okay. This is a rough sketch of what this graph looks like. All right, if you want to get a more detailed sketch, you can always plug that into Wolfram Alpha and ask it to get a sketch for you. So graph y equals, so what was this one? It was 49, 4x minus 8, oops, 4x minus 8 divided by x minus 4, x plus 1. So, when you type in your, the question query, you give it here, it tells us, well, this is how I interpreted it, plot this, and that's what we're looking for. That's not the best graph of the function because, they've gone out too far on the x-axis. I mean, we don't really need to see that much of it, but they're trying to give you a better idea of what's going on with that horizontal asymptote. And you do need to go out pretty far, in order to get so close. So like on the y-axis, this is y equal to half. This is y equal to negative half, and then you're going all the way out to x equal to 60. So you can, from like x equal to 5 to x equal, from x equals negative 5 to x equals 5. You can specify a tighter domain on the x-axis, and there you go. There's a nice picture of it. So where's that inflection point? It appears to be at the x-intercept, where the curvature changes from curved up to curved down. Don't know if that's necessarily the case, looking at this. Well, it might be. I mean, I'd actually have to try to figure it out using calculus, but we don't know. But that's, this is the picture we've got, and this is, a more accurate one. But, this exercise helps us to understand these functions better. And that's why we're doing it. Okay, so we've got that. Let's do one more. 50. No, 57 is not the best example. Which ones did they ask us? Well, which ones did I assign? $34 and 36. Wait a minute. Oh, with 34 and 36. Oh, right. They're only asking you to find horizontal and vertical asymptotes, not to sketch the graph of those functions. That's my mistake. I want you to sketch the graphs of those. I'm gonna have to change this assignment. I apologize. I will post it. I will post it after class. That's not the problem as I was assuming it was. We want to sketch the graph of the function, not just find the asymptotes. So I'll post something different. So let's take a look then at number 50 through 55. Did you sketch the graphs or did you just do the asymptotes? Because that part's, not much to do there. So number 55. So we want to sketch the graph of the function 2x squared plus 2x minus 4 over x squared plus x. So we've got degree 2 on the top and the bottom. Right, so that tells us that our horizontal asymptote occurs at y equal to, now you look at the highest degree of x, the highest power of x on the top and the bottom. You've got a leading coefficient of 2 on the top and leading coefficient of 1 on the bottom as coefficients for x squared. So you take the coefficients for the highest power of x on the top and bottom, and the ratio of those two things, that's where your horizontal asymptote is. And of course, you'll never get y equal to 0 when you do this, because when we say the degree on the top and the degree on the bottom are the same, it means you have a non-zero coefficient for that highest power of x on the top and bottom. It's only when the degree of the top is less than the degree of the bottom that you get the horizontal asymptote at y equal to 0. So now you may be asking, well, what if the degree of the top is larger than the degree of the bottom? I'll actually give you an example of what goes on there, just to, just for discussion, not for, material that I want to put on an exam for you, but just, so we get a more well-rounded picture of what the story is here. So horizontal asymptotes, vertical asymptotes. So to start talking about vertical asymptotes, we need to factor the top and the bottom of this function. So on the top, well, does that factor? Let's see, 2x and x. Oh, well, this is x squared. Let's factor out of 2, x squared. Let me see. So x squared plus x minus 2, right, that does factor. So we get 2 times x minus 2, or it's x plus 2, x minus 1. And on the bottom, x times x plus 1. So vertical asymptotes on the bottom at x equal to 0 and x equal to negative 1. That's where the bottom is 0. Where the top is 0, that's where your x-intercepts occur. So that's at x equal to 1 and x equal to negative 2. And the y-intercept, that's at r of 0. So that's 2 times negative 1 over, oh, right. So you can't have a y-intercept because the y-axis is a vertical asymptote. Right, we're dividing by 0, so this quantity is undefined. Right, you can't divide by 0. You can divide 0. You can have 0 on the top of a fraction. Right, 0 divided in half is still 0. 0 divided in thirds is still 0. Nothing divided into equal parts is nothing in each part. And those parts are all equal. It's when you try to divide by 0, divide something into no parts, right? That's what doesn't make sense, right? Divide something, divide, 100 into 0 parts. Well, you can't. There's something there. I got to have at least one part. Different ways of seeing that, division by 0 doesn't make sense. So no y-intercept. Now we want to look at positive and negative properties. Put your vertical asymptotes and your x-intercepts on the number line. So -1, 0, 1, and -2. And if you test points here, so x equal to -3, what are we going to have here? So these terms here, or factors here, are negative, 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 and negative. So the whole thing is positive. And this one's going to alternate. I mean, you can test all of those, intervals, but this one it's going to alternate, positive, negative, positive, negative. It doesn't alternate when you start having some squares. Like some of these are squares. If that was a square, then it doesn't necessarily alternate. All right, so we've got our intercepts, we've got our asymptotes, and both horizontal and vertical. So we can get a nice sketch of the graph here. All right, so horizontal asymptote at y equal to 2. Right about there. Vertical asymptotes at the y-axis and at -1. And intercepts at 1 and -2. So here's x equal to 1, and here's x equal to -2. And then we have for positive and negative behavior, positive, negative, positive, negative, positive. Okay, so probably I'm going to need to shift this picture down. I don't think it's quite enough space to get a good drawing here. Okay, so positive and negative, and x intersect here. So it's looking like that. Right, and then, aside from this positive and negative behavior, right, we're smooth and unbroken. Now I've got vertical asymptotes here, and we're positive. So the only thing that can happen is something like that. Right, it's going to have to decrease and then increase. Not a whole lot of space to draw that, is there? Okay, vertical asymptote here, and it's positive. So the only thing really that can happen is something like this. So again, there's a lot of, not a lot, but there's definitely something that's it's this feature here. There's got to be a local minimum. It's got to be coming down from the vertical asymptote on that side and up, climbing up the vertical asymptote this way. So it has to decrease and then increase. And the question is, well, where does that happen? Okay. Well, you may say, well, it's going to happen in the middle at -1 or -1/2. Maybe, but we don't know for sure. Okay, you'd have to use the calculus to figure that out. So in order to do that, like when you learn about that sort of thing, you have to take what's called the derivative of this function, and then set the derivative equal to 0 and find out where that derivative is 0, and that's essentially where this is happening. But that's not something we're covering here. But I mean, there is a local minimum in there somewhere. And then we've got an x-intercept here, and it's negative on that side of the intercept with a vertical asymptote at the y-axis. Again, intersecting the y-axis there, and then hugging the horizontal asymptote like that. All right, so there it is. So that's y equal to this function here. Right, it's an interesting looking graph, I think. So what happens when the degree of the top exceeds the degree of the bottom? Okay, since we're on the subject, we want a more complete picture of what's going on. What happens when the degree on the top is greater than the degree on bottom? Well, remember we talked about dividing polynomials, right? So when you have a rational function, p of x over d of x, where the degree on top exceeds the degree on the bottom, then you do long division. So perform the long division. And what happens is you get a quotient. Plus, then you get this remainder over the divisor still. And what was special about the remainder is that the degree of the remainder is less than the degree of the divisor, the denominator. So the degree of r of x is less than the degree of d of x. So you've got this q of x, and that's what? That's a polynomial. It's a polynomial of some sort. Okay, degree 1, degree 2, degree 3, degree 0 even, right? Just a constant. That's when the degree on the top and bottom are the same. Or it could be degree 1, degree 2, something of that sort. And then here, what's left over, the remainder over the divisor. Here, the degree of what's special about the remainder is that the degree of the remainder is less than the degree of the divisor. Less by how much? We don't know. It's less. And as x gets very large, remember, r of x over d of x has a horizontal asymptote at y equal to 0. In other words, if x is big and positive or big and negative, then r of x over d of x is tiny, is close to 0, i.e. tiny. So if x is big, r over d is tiny, really small, close to 0. So the graph is essentially Q. The value of px over dx, so therefore, when x is big, okay, px over qx, or dx, which is equal to the quotient qx plus, this remainder, rx over dx. Well, as I was saying, the r over d is tiny. So the value is essentially just q. It's just the quotient. So is approximately equal to q of x, because this part is tiny. And what else did we say about polynomials? When x is big, with graphs of polynomials, they're always marching off to infinity, either positive infinity or negative infinity or positive infinity or negative infinity in both directions. They're always approaching the infinite, the value of a polynomial. So when x is big, the value of that is big, and the value of that is tiny. Right? So when you really want to know what's really important about the graph, it's really essentially just q. It's what's going on in the middle that is for just sort of ordinary values of x equal to 1, x equal to 0, x equal to 3, 4, 5. That's where more sort of interesting things are happening. But for large values of x, the value of the rational function p over d is essentially just the quotient. It behaves just like the quotient. So the basic idea is like this. All right, so say that px over qx is equal to a linear polynomial. Let's say x plus 1, half x plus 1, plus dx over rx over dx. So look at this right here. What's the graph of that look like? 1 half x plus 1. Looks like this. Looks like this. All right, so that's the line y equals 1 half x plus 1. Essentially, the function p over q looks like that line, except in the middle. except in the middle. So the function is going to do like this. It's going to hug that. It's going to hug that line. The difference between the rational function and that line is not that much. What's happening here in the middle? Well, you know, we're not sure. I mean, there's going to be some vertical asymptotes. There's going to be some local maximums and minimums, some sort like that. But as you go off towards infinity, it looks just like that line. It looks just like that line. So suppose you had this instead. X squared plus Rx plus, remainder over denominator. What's that look like? All right, well, what's the graph of y equal to x squared look like? Well, it's that basic parabola, yeah? So here's the graph, y equals x squared. So the graph of the rational function, y equals px over qx, is essentially the graph y equals x squared, except for what's going on in the middle. So it's going to just sort of look like that. And there's going to be some, vertical asymptotes in the middle, perhaps, something like that. So this is y equals px over qx. Let's do a little bit of experiment. Let's do a little bit of experiment. Let's look at some graphs online. All right, so let's do the graph of x. So let's put in that parabola. Y equals x squared plus some rational function where the degree on the top exceeds the degree on the bottom, like this one we just looked at. Or sorry, the degree on the top is less than the degree at the bottom. There it is. See? That's the parabola y equals x squared. There's funny stuff going on in the middle for smaller values of x, where the denominator of this function is equal to 0. So at x equal to negative 2 and at x equal to 4. So you have a vertical asymptote at x equal to 4. See that? Where I put my cursor, you see the vertical asymptote. And there's also a vertical asymptote here at x equal to negative 2. There's a local minimum and local maximum at various points there as well. So, I mean, there's some interesting stuff going on for small values of x. But when x is big, it just looks like the ordinary parabola, right? When x is large. When x is large, this bit becomes unimportant because this bit is close to 0. It's this bit that's important, the x squared. The x squared is large when x is large. This is close to 0 when x is 0. So essentially it has almost no effect on that. So it has a parabolic asymptote, if you will. Now you could graph y equals x squared along with this. Can I do that? Graph this and y equals x squared together. Let's see if it'll do it. No, oh, I even did it in a different color. But it's not showing. For x equals minus 100 to x equals 100. There it is, see? They look the same, don't they? Well, the interesting stuff is happening like inside here, but you're not really seeing it. Maybe x equal to like minus 50 to 50. We don't even need that much, 20. minus 20 to 20. Yeah, even that's a lot, maybe minus 10 to 10 to show things in a more interesting light. Right, so the red is the graph y equals x squared. That's the parabola. The blue is x squared plus that rational function. See, it's only for those values around the asymptotes here that things are, differ from the parabola. After that, it's essentially just the parabola. If you didn't have a parabola, how about just a line? Let's do the 1/2. So 0.5x plus 6 or something like that. Oops. Oh, I don't want that y equals x squared anymore. 0.5x plus 6. So here's the line y equals 1/2 x plus 6. That's the red. So x-intercept is 6, and it's got slope equal to 1/2. So here in the blue is 1/2 x plus 6 plus that rational function, right? So around where those vertical asymptotes and where like the x-intercepts are happening, right, there's some significant difference. But as you go further, as x gets large, in positive large and or negative large, the rational function essentially just becomes the line. So it's pretty neat. So this is often called a slant asymptote. So when the degree of the top exceeds the degree of the bottom by 1, you have this slant asymptote, a linear asymptote. If it exceeds by 2, then you have this parabolic asymptote. So on and so forth. All right. I'm not going to ask any homework problems on that. Make this one due on Thursday since I have to change it. But just so we had a more accurate picture of what's going on. So Thursday, that's the 14th, I guess, or 15th. 7/15. All right. I'll post that after class, and I'll mention it in the email as well to watch out for that. So on to the last chapter, chapter 4. So starting with section 4.1. So this is the last chapter. We've got how many weeks left in the semester? We've got 3 weeks, yeah? This week, next week, and the last week. So I'm aiming to have like the third exam on the 26th. So I think on the 26th, and then the final on the last day of class, the 29th. So, we'll have several days to review in between. All right, so maybe not the 26th. Maybe if I can get it on the 22nd, it would be good. That way we get a whole week to review. But we'll see. Let's see how fast this goes. So section 4.1 is on exponential functions. So we're doing exponential functions and logarithms. Somehow, you might find it confusing. Some students find it confusing, exponential functions and logarithms. I think the presentation we did this semester, should be helpful. The logarithms tend to throw people for a loop sometimes. So, if you can spend a little extra time on it and ask me for help, it would be good for you. All right, so given a positive number a, Okay, an exponential function with base a is of the form like this: f of x equal to k a to the x. The k is a constant. All right, and a greater than 0 is constant. The x in the function is variable, as usual. Okay, so common bases that are used. So 2, so 2 to the x, 1/2 to the x, that's another common one. There's this number e called Euler's constant, where e is approximately 2.72 something something something. It's another one of these irrational numbers, special irrational numbers. What's special about it, you'll learn in calculus. It's a number that's got a special meaning to it with regard to derivatives. But we'll introduce it now. So E, this Euler's constant, 2/2. Oh, also 1 plus 0r. 1 plus r, I guess, r over 100 to the x, where r is some interest rate, like r equal to like 3% or something like that. So some rate of interest. So if you're talking about a mortgage or a savings account or a CD or something, or car loan or whatnot, something like that. So these are common bases that are used with exponential functions. The most, 10. 10 is called the common base. Which base is the most commonly used? Well, it depends on the context. 10 to the x is definitely one that's used a lot. I think e is probably the one that's used the most. And then in computer science, the 2 is used a lot. All right, so for example, so let f of x equal to, let's say, 6 times, we'll use 1/2 to the x. So f of 3 is 6 times 1/2 to the third. All right, so that's 6 over 8. All right, 1/2 to the third is 1/8, so that's 6 over 8, which is 3/4. F of 10, well, that's 6 times 1/2 to the 10th. So that's 6 over, well, that's 2 to the 10th, it's 1,024. All right, so this is 3 over 512, whatever that number might be. F of minus 3, that's 6 times 1/2 to the minus 3. So that's 6 times, well, 1/2 to the minus 3 is 8 rather than 1/8, which is equal to, in this case, 48, etc., etc. Notice the value of an exponential function is always positive. That for k bigger than 0, okay, so for this constant out front bigger than 0, the value of f of x equal to k a to the x is strictly positive. It's never 0. So in particular, f of x is not 0 for any x, and f of x is not less than 0 for any x. So exponential functions are strictly positive, as long as that k is positive. I mean, that could be that k is negative, in which case it's always negative. Usually not. Usually you're modeling positive values, positive quantities when you're dealing with exponential functions. What does the graph of an exponential function look like? Oops. So if you have f of x where equal to k a to the x, where k is positive and a is bigger than, so the sort of big difference in what exponential graphs of exponential functions look like is when so a is always positive with an exponential function. It simply doesn't make sense to have it negative because you can't just plug in. I mean, you can define this, negative 2 to the fifth. That's negative 2 times negative 2 times negative 2 times negative 2 times negative 2, which is minus 32. Like, you can have a negative base with an integer exponent, but a negative base with a non-rational number as an exponent, it's not, you can't define it. With a rational exponent, you can, but then you got to watch out for positive and negative, even and odd values. Like when you're doing this, like that wouldn't be defined. This would be. So I mean, it's opening up a can of problems that you don't wanna open. So the base is always positive. Okay, the big sort of difference occurs when the base is bigger than 1 or less than 1 or equal to 1. So the graph of the exponential function looks like this. So other than that, they all look like really the same. So here's k. Ugh. So you have the sort of a horizontal asymptote going off to the left, and then it just marches upward to infinity like that. I put that stupid arrowhead, and I shouldn't. So this is the graph of an exponential function. So I don't need that. Get rid of that. For a bigger than 1. So k a to the x. So this is k right here. So y equals k a to the x for a bigger than 1. K a to the x for k less than 1, it looks the same, except it's reflected around the y-axis. So here, see if I can get it better. There we go. So this is y equals k a to the x for a less than 1. So a less than 1 looks like this. A bigger than 1 looks like that. They're exactly the same, except they're just flipped around the y-axis. When you have different bases, it just makes it more or less steep. So different bases, both positive, it is going to look like this. So this is like y equal to 2 to the x. And then y equal to 3 to the x would look a lot the same, but just kind of climbing up faster and heading down here faster. So y equal to 3 to the x. So the larger the base gets, the steeper the curve is. But it always just kind of looks the same as we have it here. And that's just a terrible picture. This part of it came out bad. There we go. And then when the k is 1, this is 1 right here. So that's a graph of an exponential function, the basic form of it. Oh, okay, it's 1058. All right, so tomorrow we'll continue on section 4.1 and maybe get into 4.2, okay? All right, everybody, have a nice day.